This is flow process test. Level process also consists of flow process because we are controlling flow rate to control. Here, this is to control flow rate. This is to control flow rate alone. That is called flow process. Here, it has one sump. From the sump, a pump is used to pump. Instead of using a valve, you can use valve to adjust the flow rate. In level process, yesterday we have seen that a valve is used to adjust the flow rate. For that, we are giving 3 to 15 psi pneumatic signal to the valve to adjust the flow rate. That is by adjusting valve opening, we are adjusting the flow rate in the level process. But here, we are going to adjust the speed of the pump. If we adjust the speed of the pump, we can adjust the flow rate. So, the pump speed adjusted to adjust the flow rate from 0 to 100%. That is coming through this rotameter. You can notice the flow rate in this rotameter. Here, now you can notice that the flow rate is about 12 LPM, liters per minute, or about 3 GPM. So the controller output is about 40%. 40% means the speed of the pump is about 40% of its full speed. 40% of its full speed. That's why 40% flow rate we are getting. 40% flow rate of maximum flow rate we are getting. So here, this rotameter is to see the flow rate. That's all. There is no relation between controller and this rotameter. It is only a local indicator to see what is the flow rate. To see that what is flow rate. So, if you want to control the flow rate, then what should we do? We should measure the flow rate. We should measure the flow rate. We need a signal, electrical signal for that flow rate. That's why there is a orifice plate is there. You have studied about orifice plate? Elsewhere? Industrial instrumentation? Not yet. Orifice plate is placed here. It is nothing but here a plate with lesser diameter than the pipe. That's all. The plate with a hole that has lesser diameter than the pipe. That's all. That's why there will be a pressure drop. There will be a pressure drop. Whenever you put some block in the tube, there will be a pressure drop. So there will be a pressure drop. There are 2 tappings are taken. Before that orifice plate, pressure will be higher. After the orifice plate, pressure will be less. There is a relation between flow rate and pressure drop. From that we can find the flow rate. So 2 tappings are taken from this orifice plate and it is given to the DC transmitter. This is the DC transmitter. Differential pressure transmitter. So 2 tappings are taken from the orifice plate, across orifice plate, and it is the upstream pressure is given to higher pressure side the DC transmitter, and the tapping is taken after the orifice plate is given to the low pressure side of the DC transmitter. In turn, DC transmitter gives 4 to 20 milliamps as flow rate varies from 0 to 100%. What is meant by 0 to 100%? If flow rate is 0%. Flow rate is maximum 100%. As flow rate varies from 0 to 100%, this DC transmitter gives 4 to 20 milliamps. That 4 to 20 milliamps is given to this PID controller. So it will read the flow rate from 0 to 100%. So this DC transmitter is a 2-wire transmitter again, as we have seen yesterday. This 2-wire transmitter needs a power supply. Any device need a power supply. No? 2-wire transmitter means the 2-wire carries both signal as well as power supply. So there are only 2 wires. That takes power supply, 24-volt power supply. That is one end of that power supply is connected to one end of DC transmitter power, and another end of the DC transmitter signal line is connected to the load Your load is 250 ohm resistor across the PID controller. One end of the ends of 250, the other end is connected to negative terminal of power supply. So the power supply, DP transmitter and 250 ohm are in series. As the output of the DP transmitter, already we have seen that it is 4 to 20 milliamps, as flow rate varies from 0 to 100%. What is the potential drop across the 250 ohm resistor as the current varies from 4 to 20 milliamps? 1 to 5 volt. 1 to, for 4 milliamps it is 1 volt, for 20 milliamps it is 5 volt. Its voltage is varies from 1 to 5 volt. So we configure this PID controller such a way that the process variable, the variable to be controlled. What is process variable? Variable to be controlled. That is flow rate is given as 1 to 5 volt. That the PID controller reads that 1 to 5 volt as input for the process variable and displays in percentage. Displays in percentage. For 40% the controller output, the flow rate is about 20%. That's why it displays 70 to 20%. Flow rate is about 20%. Now we give the process variable as input to this PID controller. If you give, suppose this PID controller is closed loop, if you give set point to that PID controller, it compares the process variable with set point. Suppose set point is say 25%. The actual flow rate is 20, means there will be error of 5%. Based on that, it will generate some controller output that will be added to the bias value. That will be added to the bias value. That is given to the pump to vary its speed. That 420 milliamps, because the output of the PID controller is 420 milliamps, depends upon the error. That 420 milliamps cannot drive the pump. So pump, how the speed of the pump can be varied? The pump is driven by a 3-phase induction motor. The pump is driven by 3-phase induction motor. So the 3-phase induction motor, the speed of the 3-phase induction motor can be varied by varying the frequency. They vary in the frequency. What is the relation between speed of the pump and the frequency? What is the relation between frequency of 3-phase power supply and the speed of the pump? What is synchronous speed? Relation for synchronous speed. 120 by P. 120 is the frequency by P is number of poles in that motor. So both 120 and P are constant. That's why it is directly proportional to frequency. If you vary the frequency, speed of the pump can be varied. So this 420 milliamps can be used to vary the frequency of power supply. So this is the VFD. Here we show this. This is the VFD, variable frequency drive. Variable frequency drive. For that variable frequency drive, the input is 4 to 20 milliamps. The output of the variable frequency drive is it gives 3-phase power supply with variable frequency. The the input signal varies from 4 to 20 milliamps, the frequency varies from 0 to 60 hertz. 0 to 60 hertz. So as frequency varies from 0 to 60 hertz, the speed of the motor varies from 0 to 100%. 0 to 100%. So the VFD, power supply to that VFD is given by single phase power supply, but it gives 3-phase output. This is a power electronic device. Power electronic device. What are the inputs to that power electronic device? Power is given as single phase, 50 hertz power supply is given, and the signal input is 4 to 20 milliamps. The output of the VFD is power signal is this is a 3-phase power output. A single phase it gives 3-phase power supply with variable frequency. As the signal varies from 420 milliamps, it gives 0 to 60 hertz frequency, but constant output voltage. But constant output power voltage. That power is given to this motor. It is connected to the pump. It is coupled with the pump. That's why the speed of the pump varies from 0 to 100%. As signal varies from 4 to 20 milliamps. Now, how the closed loop is formed? Now, let us see. From the sump, this pump comes the water through this pipe. There is one orifice plate. The pressure drop across the orifice plate is taken and it is given to the differential pressure transmitter. The differential pressure DPT differential pressure transmitter gives 420 milliamps, it depends upon the flow rate. That 420 milliamps is given as feedback to the PID controller, as a feedback to the PID controller. If you give the set point to that PID controller, it compares with the actual value, depends upon the error, the PID controller controls the flow rate through VFD. So it gives its output, that 420 milliamps of PID controller given to the VFD. VFD in turn adjusts the speed of the pump. It is a closed path. The flow rate is measured, it is given to PID controller, the output of the PID controller is given to VFD. VFD in turn gives its output to the pump, so it is a closed path. So it is a closed loop control. This is the setup. The sump, pump, then RFI split, it measures the flow rate and it gives its output to the PID controller. Then PID controller in turn gives the output to the VFD, variable frequency drive. It drives the motor. So it is a closed path. Closed path is established. Now we are going to see how to do the closed loop control for this flow process that we are going to see. So it consists of three parts in the level process. First one is obtain the mathematical model of level process. Yesterday we have seen mathematical model of level process. Then from the mathematical model we are getting the tuning parameters for the PID controller based on Ziegler-Nichols tuning parameters. Then by using that tuning parameters we are controlling the level by using a PI controller. That we have done yesterday. Similarly here also we are going to use the same PID controller but with Ziegler-Nichols tuning parameters, but the tuning method is different. Here we are going to use the closed loop method. We are going to use closed loop method. Then in level process we use the open loop method. We put the controller in open loop. So the level process is in open loop. We got reaction curve. From the reaction curve we obtained the mathematical model. From that mathematical model we obtained the Ziegler-Nichols tuning parameters. We enter the tuning parameters. Then we did the closed loop control by transferring the controller mode from manual mode to auto mode, that is open loop to closed loop. Then we did the two things. One is either servo response or regulated response is done. That's all in level process. Here we are going to tune by using closed loop method. Already we have seen that from third order process onwards in a closed loop, if we go on increase the gain, at one point it crosses J axis. In root locus we have seen. We draw the root locus for that. We go on increase K, controller gain. If you go on increase the gain of the process, in other words controller gain or process gain, at one point it crosses J axis. For particular value of K, it is exactly on the J axis. It means what? It will exhibit sustained oscillation. The poles are on the right hand side, what will happen? Process becomes unstable. In control system you have seen, the poles are on the right hand side of S plane, the system will be unstable. If it is on the left hand side, system stable system. If it is exactly on the Z axis, neither stable nor unstable, marginally stable. It exhibits sustained oscillation. Already we have seen in an oscillator, in electronics lab, we are adjusting R and R to place the poles exactly on the J axis so that it exhibits oscillation. Sinusoidal oscillators we have seen, RC oscillator, RC phase shift oscillator we have seen, then Colpitts oscillator, then Ungar oscillator. In all cases we are adjusting some parameters, some resistances, so that the poles exactly on the J axis. Similarly here also we are going to find what is the maximum gain we are going to see. For maximum gain, what will happen? Here also it will oscillate. The flow rate will oscillate. How to see that how the flow rate oscillates? If the value is there, you can see the stump goes up and down. So that it oscillates, we can see. Similarly here also we can see that this float will go up and down. As go on increase the gain in closed loop, this float will go up and down. But if you further increase, the system should become unstable. before that, what will happen? There will be a oscillation. After that, there will be limit cycle. Limit cycle means it is non-linear behavior. This what will happen? This float will go up and stays there for some time, then come down. The float goes and immediately come down means for which that gain is Kmax. If you further increase that gain, it goes up and stays there for some time, then it comes down. So we have to increase the gain continuously. At one point, it goes up and immediately returns. If you any further increase in controller gain, there won't be any increase in span of this oscillation, but it goes there and stays for some time, then come down means it is limit cycle. It should not be a limit cycle, it should be sustained oscillation. We have to find the gain of the controller for sustained oscillation. That gain is called Kmax. You have to find the Kmax to find the Ziegler-Nichols tuning parameter. That we are going to do. We will put the controller in closed loop with P only controller. Then you will go on increase the gain. At one point it will exhibit sustained oscillation, not limit cycle, sustained oscillation. That Kmax will note down. Then what is the period of oscillation we have to find? How to find the period of oscillation? Period of oscillation means maximum to minimum, again maximum one period. For that, how much time means this float will go up, come down, again come to that point. What is the time taken for that? That is one period. If you know that time taken for one complete period is called TU. Why U for ultimate period or maximum. So the TU you will know means you can find the tuning parameters. There are some set of thumb rules given by Ziegler-Nichols to find the tuning parameters. If you know Kmax and the TU means what? Ultimate period. For Kmax, what is the period of oscillation we have to find? How to find the period of oscillation? If we measure the time for one oscillation, there will be error. That's why we will allow the float to oscillate for 10 times. 10 times, but note down the time. So divide by 10, you will get the time for one oscillation. There will be less error. There will be less error. So we know TU, we know Kmax. From that we can find the tuning parameters. In some controllers, the controller gain will be in terms of K. In some controllers, it will be in terms of proportional band. There is a relation between controller gain Kc and proportional band. Kc equal to 100 by Pb, or Pb equal to proportional band equal to 100 by Kc. That is the relation between these two. They are inversely proportional. This controller is with proportional band. This is made such a way that we can enter proportional band, not controller gain. So we can find the relation, we can enter the controller gain. So or we can directly find the PB itself, because inside if you want to increase Kc, you have to decrease PB. You have to decrease PB. If you go on decreasing PB means you go on increasing Kc. At one point it will exhibit sustained oscillation. That point we have to find. Then we have to find TU. Then we have to enter the tuning parameters and you have to do the closed loop control. Then what is the first step to do that? First step is we have to do only proportional only mode. For that we should know how to operate this PID controller. The red display indicates the process variable, percentage process variable. Below this it indicates the set point or controller output. The controller output is 43%. It is in closed loop. We can put this in manual mode. For that, when the display is moved, you have to continuously press this enter. There are 4 keys are there. There are 4 keys. The first key is escape, like your keyboard escape, like that it's escape key. And there is 2 up arrow and down arrow keys. The first one is down arrow, another one is up arrow. Then enter key. Enter key is to enter something. If you modify something, you press enter, then it will accept. That's why it can be called as enter key. So escape key, down arrow, up arrow, and enter. The 4 keys we have to use. So if you press once that escape key, the display will change from set point to controller output. Anyhow, the top display will be always process variable. Always process variable. If you press this once, it displays controller output. O for controller output. Controller output is it is in closed loop. That's why it is slightly varying. It is in closed loop. To change from manual mode to auto mode, when it displays the controller output, we have to continuously press the enter key. If you continuously press the enter key, it will transfer from manual mode to auto mode or auto mode to manual mode, vice versa. Now it is in auto mode, that's why I want to continuously press this enter key. When it displays O, now it's blinking, you know. If you see closely, you can see that MAN below that indicator. It means manual mode. So now it is in manual mode. There won't be any change. The output of the controller remains 44. The output of the controller remains 44. It means it is in open loop. But in theory, if there is no feedback, we are saying that it is open loop. Here also, if you put in manual mode, it won't use the process variable to give controller output. It's also virtually open loop, you know. So if you put the controller in manual mode, it won't use the process variable to generate controller output. It means what? Open loop. Now it is in open loop, that's why the output of the controller is constant. Now only you can vary the controller output. If you press increase, now it is increasing, no? If I press the up arrow, it is increasing. If I press the down arrow, it is decreasing. So we can adjust the controller output. So in manual mode, we can adjust the controller output. Based on that, the flow rate will vary. Now let us see. If I increase the, you can notice that it is increasing, no? It is increasing. The speed of the pump also increases. Now I gave 65%. Now the flow rate is increased from 12 LPM to 20 LPM, meters per minute. So in manual mode, we can adjust the controller output manually. We can adjust the controller output manually. Now again I am reducing to 40. Suppose you want to enter some controller parameters. What is controller output in closed loop? M of t equal to controller output equal to Kc. Kc means what? Controller gain. Kc multiplied by E of t. It is only for proportional controller. Kc multiplied by error means the output of the controller is proportional to error multiplied by Kc. Suppose if it is PI controller means M of t equal to Kc multiplied by error plus Kc by Ta, one constant. Kc by Ta, where Kc is the proportional gain divided by Ta means integral time. Ti, I suffix indicates integral time. So Kc by Ta multiplied by integral of E of t. Already we have seen in the class that I mode is required to remove steady state error. Already we have seen. So there are two parameters we have to find, Kc and Ti, by using K max that we are going to find for this K max and Q. We can find the tuning parameters. To do that, we have to check whether the controller is in proportional only mode. Proportional only mode. So, while doing that closed loop tuning, the first thing is we have to put the controller in proportional only mode. There should not be integral mode. Any integral mode should not be there. That's why we will enter into that parameter mode. To enter into parameter mode, the display must be changed to set point. If you continuously press this escape key, it will enter to that parameters mode. Yes, parameter setup mode. If you again and again, if you press that escape key, it will display one by one parameters. If you press again, it displays lock. Then if you press again, there is no lock, it's off. If you press again, proportional band is 192. 192 means what is Kc? Let us assume 200. 100 by 200, 0.5. Controller gain is 0.5. Kc equal to 0.5. That is the meaning. Let us make it 200. Let us make it 200. Let us start with start with the 200, so that as we decrease the controller gain at one point, we will get sustained oscillation. Start with if you do any modification, we should press enter to accept it. Press enter to accept this 200. Now, what is the proportional band? 200. It means Kc equal to 0.5. Kc equal to 100. PID equal to 200 means 0.5. Very small gain I get. Now, if you press again enter, integral mode is off. Yes, I want off because while tuning, integral mode must be off. So then again press again that escape key. Derivative mode also off. Derivative mode, we are not going to use the derivative mode for this flow process. So all other parameters you just ignore and go on pressing that. All other parameters are important, but don't change. You can learn in that study of configuring the PID. Or study or configuring the PID. In that experiment you can understand. Don't change anything here. If you continuously press this escape key, it will come out automatically. If you continuously press this escape key, it come out. Came out. That's all. Now it is in proportional. Now what we have to do is we have to go on increase the proportional gain, or we have to decrease the proportional band so that it will exhibit sustained oscillation. It should be close to. So what is the cross variable here? So let us put about something. This is set point, you know. Set point or control output? Control. 40 is set point. Set point because before this, if A is there, then it is control output. It displays set point. So now let us decrease to about 80. I can transfer from manual mode to automatic. For that, what should be the display? Output of the controller must be there. When pressing this escape key continuously, it will transfer from manual mode to auto mode or auto mode to manual mode. For that, display must be controller mode. If you want to do any parameter entering, what should be? Then escape key continuously should be pressed. That time, the set point should be displayed. So this is like mobile. This type of operations will vary from mobile to mobile. Suppose if you use a different PID controller manufacturer, some other manufacturer, then the procedure will be different. It is not unique. So we have to press this continuously. Yes, it is in closed loop, but you cannot see any oscillations here. Now let us gradually decrease the controller gain so that we can notice the oscillation here. So that this display should be changed into set point. We correct that. Continuously press this, enter it to set point. The controller is in P only mode. We made the integral mode off. Now we have to adjust this proportional band. We have to decrease the proportional till it exhibits sustained oscillation. In root locus you can see that if you go on increase K, it moves towards j omega axis. At one point it will be exactly on the j omega axis. After that it goes to the right hand side. That we can do. For that we have to continuously press, when it displays set point, we have to continuously press this escape key so that it enter into parameters, Now once again if you press, it displays locked. Once again press proportional band. Now it will decrease the proportional band. So I decreased the proportional band. To 25%. Why have I entered? Entered means it accepted. It is in closed loop. There is no oscillation. Still, it is at the same. Now let us further decrease to 150. So I press enter key. Now it is accepted 150. There is no oscillations. So further let us decrease. $125. The poles are moving towards J axis. That's why oscillation stops. It is exactly on the J axis, oscillation should be maximum. So for 75 you can notice some oscillations. But if it is in the reference side, initially there will be oscillation, or sometimes it will settle. Damped oscillation, that is called damped oscillation. If it is exactly on the J axis, undamped oscillation, continuously it will oscillate. Here you notice some oscillation, but it settles because poles are in the reference side. Further let us decrease. It stops oscillating. No, that's why we could be able to decrease carefully. So let us decrease to 65, 10, not 25. So now we decrease it to 65. Oscillation, but again settles. Again, further let us decrease to 55. Comes up to 12. Where is point? Now let us decrease slowly. The next oscillation, again it goes to 24, means it is sustained oscillation. Of course, first time it goes up to 24, next time it goes up to 23, third time it goes up to 24, means after some time it is not sustained oscillation. So that now comes to 23 and a half. Again, that it goes up to 23. So again and again it goes to 23 here it comes up to 11. But before 11 it turns up. You notice that? Last time it came up to 11. So let us further decrease. Immediately it turns back. Have you noticed that? Immediately it turns back. That is important. So let us further decrease. Okay, I am decreasing one by one. It has to get very close to geometric axis. So we should not decrease excess. It exhibits subtle oscillation. 42. Now TD is TD max. TD max is TD min is KC max, TD min. Go on increase the TD. At one point it exhibits a sustained oscillation. It's TD min. TD min is 40. What is KC max? KC max equal to 100 by 40. TD min, that is 42. 100 by 40. Let us assume 100 by 40. How much? 2.5. So the ultimate gain or maximum gain is 2.5. Now we will find the period of oscillation. Now we will find the period of oscillation. You have to see, use any mobile. For 10 oscillation, how much time it takes? You check for 10 oscillations. When it just comes back, we turn on the clock. Turn on. When it turns back, you just turn on. 10 times it should come here. For that, how much time it will take? 10 oscillations, how much time it takes? You see this? 10 oscillations, how much time it takes? No, 1 minute 10 seconds. 70 seconds. This 0.9 means almost 11. 71 seconds. 70 seconds. Recover. Times so 98 on 70 seconds. So 70 seconds. Now let us calculate the tuning parameters by using Ziegler-Nichols thumb rules. It says what is the formula? Kc equal to point for PI control, P plus I node controller for PI controller, 0.45 times Kc max. If you want to write in terms of TD min, PB equal to required PB equal to PB min divided by 0.4 equal to how much? PB min is 42. We have seen 42 divided by 0.45. How much? 93.33. So PB equal to 93. Now we have to find PI. PI equal to PU divided by 1.2. PU upon 1.2. PU equal to how much? We have seen 70 seconds divided by 10 equal to 7 seconds. Therefore 7 upon 1.2 equal to how much? 5.83 seconds or 6 seconds. 5.83 or 6 seconds. So now let us enter those values and check whether it works. 6 seconds. Now we will go for the parameters. In integral mode, we have to enter how much? 93, no? 93. 93.3 yes. 93 point. So 73, sorry. 73. Then I mode. I mode, how much seconds? 6 seconds. So so it's still oscillating. Let us slightly increase the integral current. Sometimes because of the non-divided classes, sometimes the medium with the student parameter always gives some closer values. If I notice some oscillations, that's why I slightly increase further oscillations there. So you have to increase further. 3% variation. 3%. What is the total? What is the flow rate? About 20 LPM. 20 liters per hour. What is 3% of 20 LPM? 3% of 20 LPM. How much? 20 liters. 3% of 20 LPM. 3 by 100 multiplied by 20 liters. How much? 0.6 liters. That is not much difference. So now it is settled. What is settling now? Okay. It is around the set point only. But this variation always will be there. 1 to 2% variation always will be there because of noise in the machine. Now it is settled. This is close. Suppose I change the set point to 35. Let us change to 35. What happens in the set? Hereafter I can dictate the controller. No need to adjust the controller output manually. I can say this much flow rate I want. I will say I change it to 35. The controller decreases. Last time it goes up to 30, now 37. How much we obtained? PI equal to 6 seconds and KC PD equal to 93.3 we got. That is a rough estimate. Zero indicators always give rough estimate. We have to enter those parameters and we have to check the performance. If it is too oscillatory, we have to adjust the tuning parameters around that. So if we give, now let us check that, if we give, I am entering the parameters. To get parameters, what we have to do? It should display the set point, then if you continuously press escape, it enters into parameters. How much I gave? 150. 150. So for 150 it gives better responses, but with the same PI. But it's same gives better response. That's why we can fix 115 is the tuning parameter. Tuning means what? Radio tuning is here, you know. Find the correct RC values. Like that here we are also tuning. But Zeeman can still give rough estimate. Rough estimate is PID, but for that it gives oscillatory. That's why we are increasing PID. It means we are decreasing AC because of oscillatory. And for 115 and I equal to same 6, it gives better response. Now let us keep 115 and like that you have to write in your record. So for the rough estimate gives oscillatory, that's why you increase the proportion back to 115 and it gives better response. Like that you have to write. Now let us check for servo and regulated responses. Now it satisfies 40. There is no much oscillation, but let us check for servo response. Let us decrease from 40 to 35. Whether it works or not, let us check. And now it displays set point. Now I can directly decrease the set point to 35. Now I am dictating what flow rate I require, 35. Immediately it comes very close to 35. Some oscillation after that it will settle at 35. So I am dictating what is the flow rate required through this control. That is called servo response. Now I want to do regulated response. Regulated response means I have to give disturbance. Disturbance, this is manual valve. If I open more, what it means there is a decrease in resistance in the tube. The resistance of flow rate is decreased. So if I decrease that, there is sudden increase in flow rate. What happens to flow rate also is I opened. What happens? Increased, but not this much I should increase. I should increase slightly, but anyhow, let's check for that. I disturbed it, but anyhow. I gave large. That's why the system parameters are modified. Very small. I give again. It jumps to some 3 or 4% like that we have to do. But again it will maintain. If you cannot change this process parameter, it will change. And it will not work. Adjusting this, slightly closing and decreasing the, but it will take necessary action to bring back to 35. Again it will come to 35. That is called the regulated response. So you can check. So once again some recap. The pumps water through this rotometer. So the rotometer is a local indicator. To measure the flow rate, there is a DP transmitter. The pressure drop across the orifice plate is measured by this DP transmitter. DP transmitter gives output 420 milliamps proportional to flow rate. Flow rate varies from 0 to 100%. The DP transmitter output varies from 4 to 20 milliamps. That is given to the PID controller. PID controller we are giving the set point in terms of percentage. This also gives flow rate in terms of percentage. Depends upon the error, the PID controller gives 4 to 20 milliamps. That 4 to 20 milliamps is given to VFD, variable frequency drive. The variable frequency drive, that 4 to 20 milliamps is converted into constant voltage 3-phase power supply with variable frequency. The frequency varies from 0 to 60 Hz. Based on that, the pump speed varies. The motor speed varies as pump speed. So the pump speed varies. So we can adjust the flow rate. Now, how to tune the PID controller? We are putting the PID controller in the P only mode. Then we are decreasing the proportional band till it exhibits sustained oscillation, not a unit cycle. Till it exhibits sustained oscillation. Once it exhibits sustained oscillation, we note down PD minimum and the the period of oscillation. By using Z-Vertical's tuning parameter, we are finding Kc and the TA. We are entering that and we are doing the closed loop control. Suppose for that tuning parameters, it oscillates, we will increase Kc, sorry, we will decrease Kc. In other words, we can increase PID so that the oscillation is removed, because Z-Verticals gives approximate tuning parameters. Around that we can adjust the tuning parameters. We are adjusting only Kc, we are decreasing the Kc. In other words, we are increasing to get the oscillation free response. Now we are getting oscillation free response for the PID parameters. But the tune value of PID is 93. For 93 it gives oscillated response. That's why we slightly increase to 150. For that it gives oscillation free, less oscillations. It gives less oscillation. That gives satisfactory. In other words, it gives satisfactory servo regulatory response. So we fix the tuning parameters at 115 dB and 6. That's all.